Okay, we're into mechanical properties as our final subject this year, and as there we go. Okay. As I pointed out last time, we usually characterize the mechanical properties of a material. This is how the numbers that you see in handbooks are generated with a tension test. We load a sample up. We take generally either a cylindrical or a plate-like sample, load it up in a machine, and measure the applied load as a function of the extension. Ordinarily, we control the extension in these tests. We control the displacement between the grips because that's the method of measurement that lets us generate this whole curve. What you will see for a typical ductile metal, and I mentioned last time this curve can have any one of several forms, but for typical ductile metal, which is what we'll concentrate on, the curve looks like shown here on the left. The problem with that kind of analysis is that it gives us numbers that reflect the geometry of the specimen as well as the material properties of it. We'd like to focus on the material properties. We do that in two different ways. The first and simplest way, which generates the handbook numbers, is we simply divide the change in length by the original length and use that ratio to define what we call the engineering strain. Divide the load by the cross-sectional area, the initial cross-sectional area, and that defines what we call the engineering stress. And this plot is the engineering stress strain curve over here on the right. There are three regions in this curve, what we call elastic behavior, plastic deformation up to instability, and finally unstable plastic deformation leading to eventual fracture. The properties that are measured and tabulated in tests of this sort are quite a few. The elastic modulus, in the initial part of the stress-strain curve, the stress-strain relation is linear. The slope of the curve is the modulus, Young's modulus, and that is plotted. The yield strength is a measure of the stress at which this curve begins to bend over, and we begin to get permanent deformation in the specimen. In the elastic region, we load the specimen up, let it go, it snaps back to its original length. Once we begin to get permanent deformation in the specimen, then we say the yield strength has been exceeded, and that's Y. And as I mentioned last time, there's a bit of ambiguity in what that yield strength is for a real material, because you can get a bit of plastic deformation even very early in the stress-strain behavior. Normally, we define the yield strength by convention. We draw a line parallel to the original elastic slope, which is offset by 0.2% strain, and the yield strength is where that line intersects the stress-strain curve. It corresponds to 0.2% permanent plastic deformation. The ultimate tensile strength is simply the value of the engineering stress at the peak of this curve, and that measures the highest value of the engineering stress that the sample can sustain. If I just multiply by the original cross-sectional area, that gives me the load that is sufficient to break this bar, the highest load that it can sustain. Uniform elongation is the engineering strain up to the ultimate tensile strength. Total elongation, the total strain of the specimen, and reduction in area is just the reduction in area at the final point of fracture. Those are the parameters you see measured in a tensile test and tabulated. Well, one of the things that's kind of bizarre about this whole way of doing things is the definition of the stress and strain itself. Of course, once you begin to deform the specimen, its area, its cross-sectional area is going to decrease, and therefore the engineering stress is no longer the correct stress that the material actually senses. At the same time, there's no way for a bar to know what its original length was, particularly when you strain it beyond the elastic region. So the engineering strain is kind of a strange measure too. These are not measures of true engineering properties. They're not the things that the material actually sees. They're convenient measurements, ways of measuring stress and strain for the purpose of tabulation. If we want to see more fundamentally what's going on, we change our definition of stress and strain to the true stress and strain. The true stress is simply the load divided by the actual cross-sectional area. And you can relate that rather easy to the engineering stress, since P over A0, A0 over A. A0 over A is just, well, given the fact that plastic deformation is, to a very good approximation, preserves volume. The current area and length of the specimen that is deforming uniformly are connected to the original area and length by this simple relation. And that tells us that, for example, A0 over A is the same as L over L0, which is just 1 plus the engineering strain E. So the true stress is equal to the engineering stress 1 plus the engineering strain. So there's a simple relation between the two. The true strain is a little tougher because the sample, of course, gets longer, particularly in plastic deformation. And when we get past the ultimate tensile strength, where plastic deformations become unstable and the samples begin to net, then we have an unusual and even more difficult situation to deal with, where the strain is actually changing from point to point within the region of deformation. To get a hold of those, we define the true strain in the following way. Let's let the strain, the incremental increment to the true strain, be the incremental change in length over the current value of the length. Now I can go back to this relation, constant volume. dl over L is minus dA over A, so I can measure the incremental change in length as either the incremental change in length over the actual length or minus the incremental change in area divided by the actual area. These are equivalent measures. That is the differential of the true strain. I get the true strain by integrating that. If I am dealing with a situation in which the strain in the specimen is uniform, so that dl over L is the same all along the length, then I can get the true strain by just integrating this. And I get that the true strain is log of L over L0, where L is the current value of the length and L0 is the original value. It's actually more useful to define this in a slightly different way. Substitute dA over A for dl over L, and I get E is the logarithm of A0 over A, where A0 is the original area and A is the current area. The reason that is in fact a more useful measure to use is if I go back here and I take a sample that has become inhomogeneous in its plasticity, that's begun to neck. dl over L, this log of L over L0 no longer makes sense because the strain obviously varies from point to point. But at every point along the bar, assuming its contraction has been uniform, and that's generally true, I can measure the current cross-sectional area, I know what the original cross-sectional area was, so I can actually measure the stress from point to point through the neck region. So you can get hold of the true strain even when the strain is non-uniform, as for example in the neck specimen. The relation between the engineering strain and the true strain when the specimen is deformed uniformly is given fairly simply. The true strain is the logarithm of 1 plus E. Okay, and given that, these are our various relations between the true stress and the engineering stress. The true stress is the engineering stress times 1 plus the engineering strain. The true strain is the logarithm of 1 plus the engineering stress, and here are just the inverses of those. Here's a stress-strain curve plotted true stress versus true strain. You'll notice something very, very different between this curve and the engineering stress-strain curve. This curve shows no maximum. Only bizarre materials will ever show you a maximum in the true stress versus true strain. It yields and then hardens and hardens and hardens with strain all the way to the point of fracture. So this maximum that you see in the engineering stress-strain curve is in a fundamental sense a spurious maximum. It does not correspond to the apparent real behavior of the material, but rather to the influence of plastic instability, which in a sense reflects the geometry of the bars, which you'll see. So given that this curve is real, this one is not, and this one is physical, and it's fundamental in its variables, this one is not, and the two curves look very different, why on earth does everybody tabulate this one instead of that one? Very simple reasons. Handbooks of data are produced for engineers, not for fundamental scientists. If you're an engineer designing a building or a bridge or something of that sort, you end up really caring about two things. One thing you really care about is the elastic region back in here, because almost no engineer ever designed something to operate outside its elastic region. Otherwise it would deform, and if your car were designed to go out of elastic region when you were driving down the road, it would look like Dolly's clock in no time at all, and would not be a functional vehicle. So virtually every operating piece of machinery, every structure is designed in the elastic region. In the elastic region for these metals, the total strain is very small, and you can easily show that the engineering stress and engineering strain are identical to the true stress and true strain. It just doesn't matter which one you use. Since it's easier to measure engineering stress strain, that's what people do. But there's another reason too, which particularly the other thing that you care about in all the way up to the yield strength, it really doesn't matter. The yield strength is with very, very few exceptions, the yield strength is the same in both representations numerically, because the strain at yield is very small, so the two numbers are the same. But the other thing you're going to design to if you're an engineer is fracture. You don't want your bridge falling down. You don't want your building flipping over in an earthquake. So you're very concerned about the highest loads that it can take, the loads that would cause it to fracture, and that's the ultimate tensile strength. Well, if I go back here to the engineering stress strain curve, I got two things. One is the ultimate tensile strength is obvious, and the second is when I design my bridge or my building, I design it to an original cross-sectional area. I mean, I specify the beam I'm going to make it out of. The beam has a cross-sectional area. From the ultimate tensile strength, I can immediately figure out the load that beam can take before it comes apart. From the true stress strain curve, it's actually very difficult. I can extract that information. I'll tell you later how to do it. But it's actually really difficult to get it, and I need a completely new analysis in order to extract that information. So from the point of view of the engineer who cares about the modulus, the yield strength, and the ultimate breaking load of a specimen that has a pre-specified geometry, the engineering stress strain curve contains the information that you need to use. So that's why we use that. If you're talking about fundamentally what's happening in the material, you don't want this, because beyond the elastic region, it's not really telling you what's going on fundamentally. If you want to know what fundamentally is happening in the material, you have to flip over here to the true stress, true strain curve. And this is the way to do it. So we have two ways we measure stress and strain. One representation is useful for design engineering purposes and is almost universally used for that purpose. It governs the handbooks. The other is useful for more fundamental investigations, since it gives us insight to what's really happening in the material, and that's the true stress, true strain curve. All right, let's now go through elastic deformation, plastic deformation, and fracture. We'll begin with elastic deformation. Elastic deformation is the simplest kind of deformation. To a certain extent, it's obvious and kind of boring, you might say, but this is where engineering lives. You do not design structures, or you very, very rarely design structures to deform plastically or break. You design them to operate quite happily with no long-term deformation. That means you design them to work in the elastic region. That's where engineering design is done. So it's important to understand elastic deformation first. There are two important features of the elastic region. The stress-strain relation is linear. Stress is proportional to strain, and the strain is recoverable. You let the sample go, it snaps back into its original configuration. As I pointed out last time, there's an interesting history here, but that's it. And the recoverability of the strain is something that, if you're going to use that, you better be very careful about what kind of strains you're really talking about. Because in real materials, you get at least a little bit of plastic deformation from the very beginning of loading a specimen. This Hooke's law is, of course, deceptive as well. I won't go into it in this course beyond just the two things, but in fact, the stress is in a material. The complete stress is a second-order tensor, 3 by 3. I have 3 directions in which I can pull. I also have shear stresses, which can operate on 2 directions on each surfaces. So there are a grand total of 9 possible components of the stress. The stress has to be symmetric. Only 6 of them are independent, but basically this is a 3 by 3 tensor. The strain is also a 3 by 3 tensor, 3 perpendicular extensions and 6 shears, as I'll show you in just a minute. So the real elastic equation relates a 3 by 3 stress to a 3 by 3 strain. That means, of course, only 6 stresses, 6 strains are independent. That means I have a total of 81 elastic moduli, of which a maximum of 36 are independent. So the most general case of elasticity, you're dealing with a rather complicated world. In fact, and this is one of the reasons that we do this, almost all the materials we use in engineering, and I've said this in connection with other devices, other materials properties, virtually everything we use in engineering are highly symmetric materials in which we take advantage of the symmetry of the material to simplify the number of independent properties. We have a cubic material. Instead of having 9 diffusivities, we only have 1. In elasticity, we get that same kind of simplification. It's a little bit more complicated because we're dealing with second-order tensors rather than vectors. But in fact, if we take a cubic material, there are not 36 independent elastic moduli. There are only 3. And if we go to the case that we most commonly have in engineering, where we have an elastically isotropic material, either because it's an amorphous material like a glass or polymer, or because it's a polygranular solid, then we only have 2 independent elastic moduli. And we'll assume that that's the case. In fact, virtually everything you will see, if you pick up textbooks on the elastic analysis and so on, assumes isotropy, assumes elastic isotropy. So there are only 2 independent moduli. That is a bit deceptive, and you have to be a bit careful with that too. I'm not going to belabor the point, but let me just warn you. We generally, structural materials, structural metals, structural ceramics, are isotropic because they consist of many, many randomly oriented grains. And the average of those grains, since they're equally likely to point in all directions, is an isotropic behavior. However, when materials are processed, it will very often happen that the processing leads to what we call texture. That is, the grains are no longer randomly oriented. They tend to be preferentially aligned in certain crystallographic directions. And when that is the case, you can no longer assume complete isotropy, and you have to take account of the texture in predicting the properties of the material. Doing that is beyond the scope of this course, but let me just warn you that it's there. We're going to assume that materials are isotropic. The importance of elasticity, engineering design, almost all structures and devices are designed to remain below yield, and that's codified in the design codes. Static structures tend to be designed to the boiling pressure vessel code of the ASME, and that generally will say the stress can't get above 1/3 the yield stress. You don't want to risk having plastic deformation of a tank, which might lead to failure. In things like turbine blades, springs, and so on, moving machinery, you want to put more stringent requirements that keeps the stress very far below the yield strength so that minor perturbations of the system will not cause plastic deformation. If you have a turbine and you begin to get plastic deformation in the blades immediately run into the turbine wall and start cutting it up, and before long you don't have an operating turbine anymore. So you have to stay way below the yield strength, those kinds of things. Elasticity is also important in the way that it produces failures in materials. We don't ordinarily think of elastic failures, but there in fact are those. The failures in materials, failures that happen because of elastic instabilities that occur, and force failure, even though the material never sees a load outside the elastic region until it actually starts to fail. There are three situations here. The first is kind of interesting in a fundamental way. If you ask yourself what determines the ultimate strength of a material, what is the strongest a material could possibly be, that is governed by its elastic moduli. Because when elastic moduli are governing the stretch in the bonds in the material. And if I take a material and it doesn't have a single defect in it, and I say let it be as strong as it can possibly be, what that means is I pull on the bonds and I pull on the bonds until the bonds themselves become unstable. And when the bonds become unstable, the material can't hang together. So that is the ideal strength. Interestingly, it's been true, we started a program here, guys, 12, 15 years ago. The ideal strength of a material, elastic instability, is about the only mechanical property that you can, by God, calculate from first principles. Given advances that happened some years ago, you can take the crystallography of your material, you can throw it in a computer, you can crank and grind and solve Schrodinger's equation, and actually predict the elastic stress strain curve all the way up to failure. And in fact, I don't have time to go through it in this course, but there's some fascinating things that you learn by just exploring the ultimate strength of materials. Buckling. The ordinary way that buildings fail in earthquakes, for example, or that cars dent. When you dent an automobile, yeah, you deform it plastically, but it is not exceeding the yield strength that does that. If you take a column, the classic example, and you push down on it, the column will bow out. Because the column is bowing out, the angle, the restoring force from the column, is tilted with respect to the angle of the load. And if the column bows out enough, the situation becomes unstable, and the column will collapse by buckling. What happens is it can no longer support the load elastically, and it just bows out catastrophically, and either breaks or buckles in half. You've seen that happen before. It's what happens to a propeller when it hits the ground in an airplane crash. It ends up nicely buckled. Buckling is the usual way buildings fail in earthquakes. The columns don't shatter, they buckle because of the displacements that they have to sustain. And that's denting an automobile. If you dent an automobile, take your fist, for example, something you could do now, but you sure couldn't do when I got my first car. You press on the fender. You can press on it hard enough that you get a crimp developing at the edge, and you get a permanent dent in there. And that's a buckling problem. You pressed it until the pressures become elastically unstable, and that's produced the hinge in the dent in the material. Flutter failures. That was the famous loss of the piece of the army of Napoleon back in I doubt many of you have been in the military, but if you ever were, and you're marching along, you come to a bridge. First thing you do is break cadence. You don't go hut two across the bridge. You just walk randomly. Very good reason for that. Napoleon lost a good piece of an army while marching into Italy. They came to this bridge, they go hut two, and it was right on the vibrational frequency of the bridge, so the bridge just collapses, and his army with it. Flutter failures are vibrational instabilities are big problems, and oh guys, when I first started flying to college, the first jet plane that was available commercially in the United States was probably Lockheed Electric. And they went into the air and they probably started falling out of the sky. And the reason in that case was Ural mode. There was just because they in those days could not explore the full range of possible operating parameters, there was a situation in which the vibration coming from the prop jet would couple to the vibration of the wings in mode, a normal mode, and the whole thing would go unstable and the wing would come off. They lost several planes before they finally figured out what was happening and solved that. Lockheed Electric, by the way, is still flying. It's the Navy's P-3 Orion, which is the primary search plane. A lot of the searching for this thing down in the South China Gulf of Australia is being done with P-3 Orions. That's a flutter failure. These are failures that are elastic in nature. You can break materials without ever calling their plasticity or even their fracture toughness into play with these elastic failure modes. Well, if I have an isotropic material, I really only have to cite two elastic constants to fully describe its behavior. And those two can be revealed in a simple tensor test, and they can be taken to be, they usually are taken to be these two. First is the Young's modulus, which we've already talked about. If I pull on the bar and measure its elongation under a given stress, I've got to fix this thing. The constant of proportionality is Young's modulus. That's one. The other, if I pull on the bar, it will ordinarily get thinner. And the degree to which it gets thinner, the strain in the I'm pulling in the z direction, so I have a strain in the z direction. The strain in the x and the y directions are proportional to the strain in the z direction. And the constant of proportionality nu is called Poisson's ratio. Another way I can look at this is just the volume change. If I just add up the strains in the x, y, and z direction to calculate the change in volume, the fractional term change in volume is the strain in the z direction multiplied by 1 minus 2 nu. So the Young's modulus governs the elongation, Poisson's ratio governs the lateral contraction. There are actually 4 kinds of stresses that we have to be kind of concerned about that are applicable to materials. The 4 common stress states are the following basic stress states. Uniaxial tension is with my tensile bar. I just pull in one direction on the bar, get its response. Hydrostatic pressure, suppose I take a cube, I just put it in water or put it in the atmosphere. The pressure will impose an equal load on all of its surfaces. So hydrostatic pressure or hydrostatic compression is a situation in which I have the same stress in all 3 perpendicular directions. Simple shear